All right, West Coast, Jeff Johnson here. We're discussing already, and I just about missed my cue. I'm joined in studio here by Jackie Windh. I'm gonna let you introduce yourself because I've introduced you a couple of different ways in the past. And I think it's all been good, but I'd like to hear how you set yourself up.
Well, that's putting me on the spot, but all right.
A little bit.
Yeah, I think a lot of people in the community know me. I am interested in a lot of things, so a lot of people know me as a photographer and writer. And I think a fair few people know that before that I worked as a geologist. I have a PhD in geology, and my specialty is structural geology, which is the study of folds and faults and fractures in the Earth crust that are caused by plate tectonics. So, of course, when one of those things moves, that's an earthquake. So that's really closely related to what I did my PhD in. So it's not, I've got both my concern for the local community, which people know I speak out about in a lot of ways, but I also have this very specific knowledge about earthquakes and faulting and the effects of them.
So you have that background. Let's open with some background conversational here. We're talking about what was in 1700 referred to as the Cascadia earthquake, or that's how they refer to it now. I guess, how do we know, first of all, that this occurred in 1700, and what's the history behind the development? How did it occur, and how did it affect our region?
Well, it's a really interesting thing how people know exactly. Today, the reason we're talking about this today is the 310th anniversary of that earthquake. It happened on January 26th at 9 o'clock p.m. in the year 1700. And as most people know, that was long before there was any European settlement here. Of course, there are lots of native communities here, but they didn't have a written record. So they've passed down in their communities this oral history of this big earthquake, and it wiped out a village on Pachina. They've got a very specific oral history of it, which you can kind of back calculate how many generations ago, but there's no exact date to it. They say the shaking happened at night in winter. So scientists have been doing studies, geologists mainly, and one of the big things they did is they did mud cores in the mud flats. So they just get a little auger and they core down and pull out these layers of mud from the mud flats. And Browning Passage right here, just up the inlet from Tofino, is one of the key places where they did these studies. And other places that people will know up and down the coast, like Canham Lake between Hot Springs and Heshquit Harbor, is another place where they've done these studies, because that's a really low-lying lake right behind the beach. So the tsunami flooded that lake.
With sediment from the ocean.
Yeah, so whenever a tsunami wave comes up the inlet, it's a big turbulent wave, and it's carrying a lot of sand with it, and that sand gets thrown up on the mud flats, and you guys all know what a mud flat looks like. It's got eelgrass and algae and stuff, and that sand comes up and kills what was underneath it on the mud flat. And scientists can carbon date that stuff, that decaying organic matter. They can carbon date it, which gives an exact date of when that sand layer was deposited, which is the date of the tsunami and the earthquake. I guess I can't say an exact date because there's always an error margin on it. So they found that the highest up sand level, they found there's not just one. They've augured down and found quite a few of them. The highest up one was from the year 1700, but with an error bar plus or minus 20 years on the carbon date. So they go, okay, so we know it's give or take 300 years ago that last one happened. And there are other ones below it that the dates all came out roughly 500 years apart. There's range. It could be as little as 200 and as much as 900. But there's a range in there, but it's on average every 500 years. So then, I don't remember the exact location, but it was somewhere on southern Vancouver Island. They found all of these trees that had been knocked over at the same time in the same direction by some major event, and by doing dendrochronology, which is counting tree rings. So, if you look at a cut tree trunk, you can see you might see there are 4 skinny ones, and then 5 fat ones, and 2 skinny ones.
And those are...
They relate to the seasons.
Yeah, the growth, how good the growth season was based on elements and what have you.
Exactly. So it means if you find a living tree today that's 400 or 500 years old, it'll have those growth rings from that time period. So you can start working out the pattern. What was the climate pattern year by year by those trees? By correlating with those dead trees and matching up the patterns, they can use those dead trees and work out they all died in the same year. They all died in the winter of 1699, 1700. So they've got it constrained now that carbon date, plus or minus 20 years, now they know it was winter of 1699 to 1700. And then they went to Japan, where there has been a written culture there for, I'm not sure exactly, but millennia, I think, definitely centuries. And they've been recording the arrival of tsunamis there in Japan for hundreds of years.
The orphan tsunami or whatever they referred to this particular one?
Yeah. Yeah, because it didn't have a known parent. Normally, a tsunami in Japan, there'd be an earthquake and then a tsunami, but they had this big tsunami come in with no earthquake. So obviously it was from an earthquake far away, and that tsunami came in on January 26th. And when scientists back calculate how long does it take for a tsunami wave to travel across the Pacific, they came up with 9 p.m. January 26th. So it's this really, really cool detective work.
Yeah, that's CSI stuff, Hollywood kind of, well, but obviously real world science. That's pretty neat.
And see, people who think geology is boring, this is why I think it's so cool.
I think that's pretty fascinating. So you said this, the evidence from the sediment deposits indicate about a 500-year cycle, or between 2 and 900 years, depending on the various things, but averaging out 500 years, which means that we're kind of getting into kind of the orange-red zone of it is a cycle, I guess, is what we should explain to people. It's about motion of the plates and how they're moving. They're moving at a pre-prescribed rate and whatever. So in our lifetime, it's quite feasible that we could see another one of these large-scale earthquakes in the region.
Yeah, and that's the thing. I think there's a really natural human tendency, if you think of what happens in your lifetime is normal, and what happens outside your lifetime is like, oh, this amazing freak event. Geologists are trained to think differently. We're trained to think on scales of thousands to millions or even billions of years. So yeah, if you think about it, it's on average every 500 years.
Yeah.
The last one was 310 years ago today. Yeah. So there's an average is just an average. Earthquakes, you can't ever predict the date. You can just predict what's the average. So it means there's a 50% chance it's going to come before and a 50% chance it's going to come after. So 190 years from now, the 500 years will be up. Yeah. That means there's a 50% chance that's going to come in the next 190 years, which you divide all of that up, it means there's a 10% chance that it's going to come in the next 40 years.
Yeah. Which is enough to get concerned about.
Yeah,
enough to be aware of and maybe maximize or minimize rather the threat and the potential damage to yourself and to people here on the island and on the West Coast.
It's like I take it as, okay, there's a 90% chance it's not going to come in my lifetime. Yeah. But